Hello, this video is a continuation of cycloaddition reaction. But before we get into the next concept of cycloaddition reaction, I want to introduce some of the basic stuff that you need to know to understand those concepts. So let's do a recap of molecular orbital theory, which you learned in Gen Chem. So what you learned is that we could have atomic orbitals overlapping to form molecular orbitals. Okay, so if you have two atomic orbitals that overlap, they form two new molecular orbitals. The molecular orbitals could be a bonding molecular orbital and the anti-bonding molecular orbital. The bonding molecular orbital is the one of the lowest energy. The anti-bonding is the one of the highest energy. Okay, so how do we employ this in understanding the cycloaddition reactions? So when you look at the anti-bonding, there is a node. A node is a region where electrons are not likely to be found. So the bonding molecular orbital allows for interaction of electrons, and it's the most stable. So let us move to the diene structures. So for example, in 1,3-butadiene, so 4 carbon atoms, we could use a molecular model, okay, to show the actual molecular orbitals. So when we do that, we can have the most stable, which is of the lowest energy. So we are arranging this in terms of the energy. The lowest molecular orbital, we call it psi1. Then we can have the second lowest, which is psi2. Psi2 is going to have one node. Okay. Then we can have psi3. Psi3 has two nodes. And then psi4, which is in this case going to be the least stable, has 3 nodes. Okay. When we're filling the orbitals with the electrons, we need to know how many total electrons are there. Each carbon atom is producing 1 pi electron, okay, to contribute to the bonding. So there are 4 atoms. Well, there are 4 electrons involved. So because there are 4, we follow Hand's rule exactly the way you learned it in filling orbitals, the lowest energy, all those kind of stuff. So we fill the first one until it's completely full before we go to the next. And once we go to the next, we also fill it until it is full. Okay. Then so side 3 is going to be empty, side 4 is going to be empty. So we are going to call side 3, in this case, the lowest unoccupied molecular orbital. Lowest unoccupied because it has no electron. We're going to call side 2 the highest occupied molecular orbital. Highest occupied because it is the of the highest energy level that has electrons. Now let us use what is called shorthand drawing, because this is what we are going to deal with from now onwards in this chapter. So because there are 4 p orbitals, we can use these lobes. So we can draw them in this format. Okay. So if the overlap is favorable, then we are going to have the blues on the same side, the reds on the same side, which means the electrons can be delocalized within all the 4 carbon atoms. So there is no node. Okay. So psi1 has no node. Okay. 0 node. Psi2 has 1 node. So the electrons cannot be delocalized between carbon number 2 and carbon number 3. Okay. So this is going to be the HOMO. In side 3 we said it's the LUMO. So side 3 has 2 nodes. So in other words, how to determine the number of nodes, you just consider, are you in molecular orbital psi 1, molecular orbital psi 2, psi 3, psi 4? If you are in molecular orbital psi 4, it's going to have 3 nodes. If you are in psi 2, it's going to have 1 node. If you are in psi 10, it's going to have, you got it right, 9 nodes. Okay? So psi 4 has 3 nodes. Then the way you do it is you just divide this into 2 for 1 node. You divide this to get 3 nodes, and that one gives you 4 nodes. Okay? Let us look at the ethylene. So we've done butadiene, we've identified the LUMO and the HOMO, psi 1, psi 2, psi 3, psi 4. Let us go to ethylene. Ethylene has 2 carbon atoms, so we can have the one where there is no node, and then psi 2 is going to have 1 node. Okay, so the HOMO is going to be psi 1, the LUMO is going to be psi 2. How many electrons are in psi 2? 0, because ethylene has only 2 carbon atoms. Ethylene structure is just like this. Okay, carbon-carbon double bond. So there are only 2 electrons, so psi 2 has no electrons. Now, let us look at cycloaddition reactions. In cycloaddition reactions, it's going to involve the HOMO-LUMO interaction. And this is a situation, or it's a context of the principle of conservation of orbital symmetry, where some of the reactions are going to be symmetry allowed, some of them are going to be symmetry forbidden. Okay, so the way we need to do it, we know that the LUMO, that is lowest unoccupied, the dienophile is the one that needs to accept the electrons because it is the one that's electron poor. So it must accept an electron from the diene. So the dienophiles, LUMO, accept the electron from the diene's HOMO. So we need to draw the HOMO and the LUMO for each of these. So if we start from butadiene, let's do that is 4 carbon atoms. So we can draw psi 1, which has 0 nodes. Psi 2 has only 1 node. If we were to draw psi 3, it would be like this: 1, 2, 3, 4, and then we're going to have 2 nodes, 1, 2. So there is no favorable interaction between 1 and 2, but there is favorable interaction between 2 and 3. Then there's no favorable interaction between 3 and 4. Okay, so this is going to be psi 3, which is the LUMO. But what we want is the HOMO of the butadiene to be able to get an electron to the LUMO of the ethylene. So for ethylene, we already know the HOMO is psi 1 and the LUMO is psi 2. So we are simply having one of electrons being transferred to the LUMO, and ethylene in this case needs to accept that electron. How then do we explain the concept of whether this reaction will take place or not? Now, this is something that disturbed chemists for a long time. Okay, for example, if you do a reaction to form a cyclobutadiene, okay, so use ethylene and another ethylene, and then what we expect to form is that this would go here to create a new sigma bond, then this to prompt that one to go here to create a new sigma bond. So we end up with 1, 2, 3, 4. Okay, and so you form cyclobutadiene from ethylene. Now, what happened is this reaction could happen if light is used, but not with heat. So it took a long time for people to understand why it could happen when you use heat, but not when you use light, but not when you use heat. So this concept is going to help us to understand that. Okay. Now, so what we are going to do, we take the LUMO, we take the drawing exactly the way we did it, and what I want you to focus on is the first and the last. Okay. So we know it is kind of this way. So this is this was the first one. See the way it looks like here? And this is number 4. So let's assume that is carbon number 1 and carbon number 4. You don't really need to care about that. We know they do exist, but we are looking at the orientation, the ones that are participating in the, I mean, the last two that are going to transform into a sigma bond. Okay. So what happens is we try to create an orientation between the HOMO and the LUMO. So the shorthand lobes for the LUMO, we have them here. So we try to align them. If you try to align them and you can have the blues together and the reds together, that is favorable interaction. So that reaction will occur. So for cycloaddition, this is how the reaction occurs. And then it transforms into sigma bond, and we end up with a product. Now, like I said, if we use heat, then this reaction does not occur. Now, why would that not occur? Now, let us take the HOMO of ethylene. If we are reacting one ethylene with the other, let's take the HOMO of ethylene and react it with the LUMO of the other, because we know that the LUMO needs to accept the electron from the HOMO. So if we take the HOMO and then this is like psi 1 and this is the LUMO, the lowest unoccupied is going to be the psi 2 for this one. So we expect this to occur. So what we do is we take the two and we try to align them. So when you take them and try to align them, so we want to see whether the reds would go together. Well, the reds go together. The blues don't. So when that happens, it means there's no way for them to line up. So that reaction is said to be symmetry forbidden. The reaction will not occur. However, with the use of light of appropriate wavelength, we can be able to excite an electron from HOMO to LUMO. So let us take the ethylene at the ground state, HOMO, LUMO. If we use light, we're going to excite an electron, so the HOMO is going to have an electron. What does that mean? It means that now the one that was LUMO is the new HOMO. Okay? Then we can take the LUMO, well, we can take the HOMO of one of them and interact it with the LUMO of the other one. Okay? So let us take the HOMO. So this HOMO is going to interact with the LUMO of the other ethylene. Okay? So when you do the excitation, you're going to have one of them gets excited, and before the other one gets excited, there's that interaction. So you have the HOMO for one of them, and you align it with the LUMO of the other one, and now you get very good alignment. The blues together, the reds together, and symmetry allowed. Boom, you have a reaction.